Okay, so in the last pair of videos, we took a look at the energy considerations for general motion of a particle in 3D, and now we're going to go and take a look at getting solutions in certain specific cases. One of the big classes of cases that we like to look at are what we call separable forces. Yeah, I can spell today. Separable forces. Generally speaking, when you're trying to solve systems of differential equations, you really love it if your variables separate. That makes the complexity much, much lower and much more tractable. So, if you can write your system of, if you can write the components of your forces, so keep in mind your general force is some f of position, velocity, and time. Now, each component could depend on all of the components, but if we can write it as, so we'll say if we can write this as an ordered triplet of f sub x, that's just a function of x, x dot, and t alone, no y or z dependence whatsoever. Then same for fy. Make sure that it's of y and y dot and t only. And then finally fz is a function of z, z dot, and t only. If we can write it that way, then f is separable. And that's, if it's separable, it's much easier to solve. Now, a separable force is not necessarily conservative, but if there's no, oops, let's try it like this. If there's no dependence on the derivatives of the positions, or and also no explicit time dependence. So if those are missing, then it is conservative. Okay, so we can show that. So if we can write our f in the form fx of x, fy of y, fz of z only, we can evaluate the curl of f, right? And that will give us, we'll have an I, J, K, partial x, partial y, partial z, and then we'll have our fx that only depends on x, fy that only depends on y, and fz that only depends on z. And okay, let's go ahead and start plowing the field, right? So we go and take a look at this piece here for I hat, and we take a partial y derivative of something that only depends on z. Well, that's obviously 0. And then for the negative part, we take a partial z derivative of something that only depends on y. And that's obviously 0. And we can repeat that for the other components. And we get that the curl is indeed 0. So that completes the proof that if the force is separable and a function of the coordinates only, then the force is conservative. All right, so whenever we look at some new framework, I always like to start with a nice, comfy, familiar problem. So let's go and do some ballistics. And we'll start with no air resistance. All right. So in the case of no air resistance, we can write Newton's second law of motion as mr double dot equals minus mg k hat. And for what it's worth, the m's cancel. All right. Now, we can, without loss of generality, we can confine our motion to the xz plane. You can always, the answer is going to be a parabola. A parabola always lives in a plane, so we're just choosing the coordinate system that lives in the plane. So we'll just write our r as xi hat plus z k hat. So we can take the components of our Newton's second law, like so, and that will become x double dot equals 0 and z double dot equals negative g. We can go ahead and integrate each of those once. X dot is going to be a constant. Let's call it v naught x for the x component of the initial velocity. And z dot, okay, when we integrate that, we're going to get minus gt plus a constant, and that constant we'll call v naught z minus gt. And then we can integrate one more time. And let's let the initial position be the origin, just to make our life a little easier. So then integrating one more time, we'll have that x is equal to v naught xt, and z is equal to v naught zt minus 1/2 gt squared. Okay. So we could, if we want, we can express our v naught. So there's x, there's z. There's my v naught right there. Let's say that our launch angle is alpha above the horizon. Okay, so we've got this expressed in a time-dependent manner. It would be instructive, though, see if we can figure out what kind of shape this is by eliminating time between these. So we can take this guy here and solve him for the time. We'll get t equals x over v naught x. We can then take that and stick it in there and there. All right. So when we do, we get z equals v naught z over v naught x times, times x minus 1/2 g over v naught x squared, x squared. All right. That's looking awful parabola-y. And while we're at it, we can observe that v naught z here would be equal to v naught sine alpha. V naught x would be v naught cos alpha times x minus g over 2 v naught cosine squared alpha x squared. All right, well, if we look here, the v naughts cancel, and sine alpha cosine alpha, that becomes tan alpha. And that's about as much as we can clean it up, but it's good enough for us to recognize, since it's quadratic in x, that we're staring at the equation of a parabola. Okay, so now let's go and do that problem that I at least always steadfastly avoid whenever I teach a 100 or 200 level physics class, and that's to figure out the maximum range, the angle um, for maximum range on level ground. Why don't I like doing this problem at the 100 and 200 level? It's not that it's not doable. You can do it both with and without calculus and get an answer. The problem is that it applies only for the very specific case of level ground. And when people are just learning stuff, they sometimes forget that. If you show the general case, they can get it whether it's level ground or they're firing off the White Cliffs of Dover. Either way. Just something for you to keep in the back of your mind for your future careers. Anyway, let's go ahead and do that, and let's see what launch angle will give us maximum range. So we can go ahead and say what we got from before, that z was equal to v naught zt minus 1/2 gt squared. Now, since we're on level ground, z naught is equal to 0, but that's also going to equal our z final. So we can go ahead and set that equal to 0. So we can factor, we can get a t times v naught z minus 1/2 gt equals 0. Now this solution is just t equals 0, and we're discarding that because that corresponds to where we're launching, not where we're landing. So our time where we land will be equal to v naught z, 2v naught z over g, or 2v naught sine alpha over g. So that's our time of flight. Let's call that capital T. Now our range, let's call that R, will be equal to the position at that time. So that'll be equal to v naught x times our time of flight. So that'll be equal to v naught cosine alpha times that. So that becomes 2 v naught squared sine alpha cosine alpha over g. If you're super handy with your trig identities, or if you just look them up in a table like me, you recall that 2 sine theta cos theta equals sine of 2 theta. So using that, we can get that the range is equal to v naught squared times the sine of 2 alpha. Try that again. 2 alpha over g. All right, so we're still trying to find the max range. Well, the 100 level way to do this would be to say, well, where's the sine the biggest? Well, it would be at that angle that gives me 1. So that'd be the sine of 90, but oh, that's 2 alpha, so it's got to be 45 degrees. The 200 level way to do it would be to forget your trig and go ahead and differentiate with respect to alpha and set equal to 0. So let's just do that just to see if the 100 level way of doing it made sense. So we differentiate set equal to 0. So derivative sine is, so we're going to get a v naught squared over g. Derivative sine is cosine of 2 alpha. Derivative of what's inside gives me a 2. So, alrighty then. So we can solve for alpha. We can just divide all these constants into the 0, and we are left with alpha is equal to 1/2 of the arc cosine of 0. Well, the arc cosine of 0 is 90 degrees, so it is 45 degrees, whichever way you want to slice it. Okay. Well, you know I can't leave well enough alone. So now it's time to introduce linear air drag into the problem. So with linear air drag, our equations of motion are going to become, well, for the x component, we'll have an mx double dot equals minus c1 x dot, and mz double dot equals minus c1 z dot minus mg. Okay, now right off the bat, we can guess that this is going to be non-conservative because our force law depends on the derivatives of the position and not the position itself. So although this is separated, it doesn't depend on the position, it depends on the velocities. Okay, we're clearly going to want to divide through by m, and that's so to keep from having to write c1 over m all the time, we'll just let gamma equal that. So let gamma equal c1 over m, and then our equations of motion become x double dot equals minus gamma x dot, and z double dot equals minus gamma z dot minus g. So those are our equations of motion now. And of course, the way you solve any of these things is to guess and check. Now here, what we're going to do is we'll just go ahead and hold our nose for the moment and just formally solve for x dot. Once we do that, we can go ahead and integrate the solution once to get x. So we look at this and we recognize that there's a second derivative with first derivative of x dot with some stuff in front. That is just screaming exponential. So let's guess a solution in the form x dot equals x naught dot e to the minus gamma t. And I bet that I'm guessing really good. So we'll just check it though. Sure enough, x double dot equals minus gamma x naught dot times e to the minus gamma t. Then we look at this much of it right here and recognize that that's still our x dot. And so sure enough, it checks, it matches the differential equation. So the guess was a good one. Okay, that constant for the equation in z dot here, that's going to be a little more gruesome, but not too bad. So my guess for the z dot is I'm going to guess something like z dot is equal to some z naught dot e to the minus gamma t minus g over gamma 1 minus e to the minus gamma t. Okay, that's a really, really good guess. But let's just go ahead and work it through and stick it into the differential equation and see if that's indeed what pans out. So we're going to get a minus, putting into here, minus gamma times all this stuff, so we'll have a minus gamma z naught dot e to the minus e to the minus gamma t. So I'm just working on the right hand side at the moment. Sorry, z double dot there. Or sorry, no, that's z dot there, my bad. Oh, sorry. Let me just go ahead and differentiate this. That'll be easier. So bringing down that, that's the first term. Second term, constant goes away. The third term minus a minus is a plus. When I differentiate, there's going to be a minus. So I'm going to end up with let's see, right, plus gamma over g gamma e to the minus gamma t, cancel, cancel. Oops, what am I doing? Sorry. Let's try differentiating again. So yeah, the first term goes away, second term brings this minus is already a plus. Differentiating is going to bring down another minus. So we'll have minus g over gamma, then the derivative is going to bring me a gamma, e to the minus gamma t, cancel, cancel. All right. And if I stick that back into the differential equation, it works. So, yay, that was my solution. We need to make sure, let's also check that the initial conditions make sense. So, oops, we want that black. We'll check that the initial conditions make sense. We want z dot at 0. That will equal z naught dot times e to the 0. That's good. Minus g over gamma. That looks a little scarier. Times 1 minus, oh, but e to the 0 is 1, so that term drops. So yeah, the initial conditions check. So we'll let the initial position be the origin. No reason not to. So now we're left with integrating our solutions to get it for x. So x will equal integral from 0 to t dt of x naught dot, okay, that's a constant, I could have pulled it out front. In fact, let's just do that right now. X naught dot times e to the minus gamma t. So integrating that is going to give me minus x naught dot over gamma e to the minus gamma t, evaluated from 0 to t. All right. So that will be minus x naught dot over gamma times e to the minus gamma t minus 1, or x naught dot over gamma times 1 minus e to the minus gamma t. All right, so first thing that we get out of this is that we know that our final that at the end of time we would asymptotically approach an x-coordinate. Now this is letting the y-coordinate do whatever it wants, but at the end of time our x-coordinate could go no further than x naught dot over gamma. All right. Now let's go ahead and integrate the y, or sorry, integrate the z. So z will equal, again here we can pull out, we're going to be integrating dt from 0 to t. Here we have a z naught dot e to the minus gamma t minus g over gamma 1 minus e to the minus gamma t. Alright, so this is actually going to turn into 3 integrals dt. So let's do them in turn. 0 to t dt. We can pull the z naught dot out of e to the minus gamma t, then minus g over gamma, oops, sorry, yeah, times integral 0 to t dt, then plus g over gamma integral 0 to t dt of e to the minus gamma t. All right, let's evaluate each of those individually. This one will give me z naught dot over gamma e to the minus z naught dot over gamma e to the minus gamma t, evaluate from 0 to t. This one is going to give me minus g over gamma t, minus 0 if you must. Yeah, we'll just say t. We'll leave it evaluate 0 to t. Then minus, we're going to pick up here a g over gamma squared, e to the minus gamma t, evaluate from 0 to t. All right. So this becomes minus z naught dot over gamma. Actually, I can make that a plus, and this becomes 1 minus e to the minus gamma t. This becomes minus g over gamma, just plain t. And then this one also is going to become plus g over gamma squared, 1 minus e to the minus gamma t. We can clean this up just barely and get ourselves a z naught dot over gamma minus g over gamma squared, 1 minus e to the minus gamma t minus g over gamma t. So that is our solution for z. All right. So we can once again try to find the range. So we're going to kind of do this counterintuitively. If we try going for the jugular and sticking in z equals 0 here and solving for time of flight, it isn't going to go so clean. So the trick we're going to do here is we're going to take our solution for x, actually, and we're going to solve for the time in terms of our x max. And then we'll stick it into z and hope that that works a little better. So we're going to let our x max equal x naught dot over gamma minus x naught dot over gamma e to the minus gamma t. That's just expanding out the fraction. So we can we'll rearrange a little bit here. We want to get e to the minus gamma t all by itself, so we'll do that. E to the minus gamma t, we're going to need an x naught dot over gamma for just a second longer. Put that over there, bring that over here. X naught dot over gamma minus x max. Okay, we can then multiply both sides by gamma over x naught dot. So then I'll give me e to the minus gamma t equals 1 minus gamma x max over x naught dot. And then we can take the log of both sides and solve for t. So we get that t equals minus 1 over gamma times the natural log of 1 minus gamma x max over x naught dot. And yes, physicists usually write log instead of ln. So if you see me doing that, that's what we mean. By default in physics, pretty much every log you'll ever deal with is a natural log. The only base 10 logs that you ever get are with sound intensities and with light and with stellar magnitudes. Pretty much otherwise you just don't care. Okay, so now that we've got the time of flight, we can substitute into our solution for z. So we'll have that z equals 0, because we'll set z equals 0 actually, because we want where it impacted the ground. That'll be z naught dot over gamma plus g over gamma squared times 1 minus e to the minus gamma times 1 minus 1 over gamma times the log, oops, this 1 over gamma times the log of that stuff there. Minus, still in the parentheses there, g over gamma times minus 1 over gamma times that same log again. All right. It is incredibly uninstructive to continue to try to solve this. I will just say that it is clearly the solution is x max equals x naught dot over gamma times g plus z naught dot gamma times g plus gamma z naught dot minus, so just continuing over here, g times w of e to the 1 plus gamma z naught over g times g plus gamma z naught dot all over g. Let's see, yeah, one more parenthesis, there we go. In this w function is actually called that, is the w function here is a thing called the Lambert w function. I never heard of it either until I tried working on this problem. It's the inverse of f of w equals w e to the w. So just like, so you kind of think of an analogy how, see, the natural log is the inverse of e to the x. This is the inverse of w of x e to the x, if you will. This is not a function that can be written in analytic form, but you can look it up in tables. In fact, it's a transcendental function. So anyway, I'm sorry. But it's something that you can look up in tables. So anyway, that was kind of a dead end. So let's take star here. And if we wanted to rewrite star slightly more cleanly, and we do, we could have written it as z naught dot over gamma plus g over gamma squared times gamma x max over x naught dot plus g over gamma squared times the log of 1 minus gamma x max over x naught dot. All right, that's a transcendental function, and we're not really going to get very far with it, but if we go and let this, wherever we see this gamma x max over x naught dot, let's call that u. Okay, and then we can go ahead and do a series expansion on the log of 1 minus u, which you'll remember is equal to minus u squared over 2 minus u cubed over 3, and so forth, as long as the absolute value of u is less than 1. In this case, we know it is. So we can go ahead and put that approximation into here. So now we've got 0 equaling, so it should have been 0 equals, 0 equaling z naught dot over gamma u minus g over gamma squared u, and then from here we'll have a plus, yeah, right, no, plus g over gamma squared, and then from here we get a minus g over gamma squared u from the expansion, so minus g over gamma squared u minus g over gamma squared u squared over 2 minus g over gamma cubed u cubed over 3, and we could go higher orders, but why bother? All right, one thing we get here is that these terms linear and u go away. One solution we have is u equals 0, but that's not interesting. Same reason as before. That corresponds to x max of 0, so that really is just matching the launch point. So we have to look for other solutions, so we can factor out a u from what's left here. So we'll have 0 equals, factoring out a u, z naught dot over gamma minus g over gamma squared u over 2 minus g over gamma cubed u squared over 3. All right, so we can rewrite this a bit. We can formally solve it for u as u equals 2 gamma squared over g times z naught dot over gamma, cancel, cancel, minus 2u squared over 3. All right. Now, this is where, again, you look at this and say, is that really that helpful? And the answer is no, but since we're saying that u is small, that means u squared is really small. So we can go back to doing successive approximations. So we can get our first approximation is just u is approximately 2 gamma z naught dot over g. And then we can push that back into double star. So we do, and we will get u is equal to 2 gamma z naught dot over g minus, and now we go and square this, so minus 2 times 4 gamma squared z naught dot squared over g squared, and we can clean that up, get u equals 2 gamma z naught dot over g minus 8 so minus 2/3. I dropped a 3 there. Yep. So minus 8/3 gamma squared z naught dot squared over g squared. All right. Remembering what u was to begin with, that was gamma x max over x naught dot equals that stuff. All right, so for what it's worth, we can cancel a power of gamma. Cancel, cancel, cancel. And then just times through by x naught dot. So we get x max is approximately 2x naught dot z naught dot over g minus 8/3 gamma x naught dot z naught dot squared over g squared. Now, if you recall, we already showed that 2x naught dot z naught dot was v naught squared sine 2 alpha. So let's go, and we also showed that z naught dot was just plain v naught sine alpha. So putting that in, we can finally get x max into a somewhat useful form of v naught squared sine 2 alpha over g minus 4/3 v naught cubed sine 2 alpha sine alpha over g squared gamma plus higher order. All right, so we can break this into two pieces. This piece here is the no air drag solution from before, and then this is our correction for air drag. Of course, we've been doing linear air drag, which isn't usually realistic. So, since linear air drag isn't usually realistic, time for us to really delve into it and start doing quadratic air drag. All right. It does show the power of successive approximations. So here, our Newton's second law is mr double dot is equal to minus c2 times the magnitude of v times v itself minus mg k hat. Since we're going to be we can do the same thing here where we'll let gamma equals c2 over m. So then this becomes r double dot minus gamma mag v v minus g k hat. And again, let's confine our motion to the xz plane as before. No need not to. So we get x double dot equals minus gamma. Now here's the thing, the magnitude of v is going to be the square root of x dot squared plus z dot squared. Then we have x dot, then z double dot is going to be minus gamma, that same square root, x dot squared plus z dot squared, z dot, and then we have this bit here, minus g. That's the system. Now this is not separable. And in fact, the only way you can really go about this is by numeric methods, which I've queued up here. So I went ahead and had Mathematica do the no drag case and the linear drag case just like before. So here is the solution for the no drag case, for instance. There's the z component of the velocity, and then there's the z coordinate itself, and I had similar solutions for the x and y coordinates, and we'll make the y 0 at some point. Similarly, I did the linear drag, got the x solution that we got before, got the y solution that we got before, or sorry, it's just in 3D in general, so the x and y solutions are the same. And then here's the z solution that we got before. Although Mathematica doesn't write it as pretty. And then just for the giggles, I went ahead and plotted the two of them. And for launching something at 141 meters per second at the optimal 45-degree angle, we get that the object with no drag would fly over 2,000 meters, and with linear drag would go about 800 meters or so. All right. In fact, 802 and 2,040 meters if you really wanted to get fussy. Now for the quadratic case. So again, here I just set in the differential equation that I just wrote down before and solved it. But I couldn't just do solve. I had to do desolve. I had to do ndesolve and do it numerically. So we have, again, these interpolating functions, which are a collection of points that are tied together using a mathematical construct called a cubic spline. If you're familiar with the drafting instrument, the French curve is a collection, basically this is the mathematical version of drawing a French curve through the points. Okay, so I went ahead and plotted that on the solution for that on its own axis, and you can see that we're going like 28.5 meters. I plotted in versus the other two solutions. You can't even barely see it. It's just that tiny little tick right there compared to these other two. By the way, just for the grins, here is the solution for the linear. Here's the solution that I did before that got us the Lambert W function. Mathematica calls that product log, which is another name for it. Okay, in the next video, we'll take a look at a couple more examples. We will visit the harmonic oscillator, doing it in 2D and 3D. We'll do an example with electric and magnetic fields so that we can play with more velocity-dependent forces. And then we will explore constraints.